Okay, in this example, I've got two gears. One has a moment applied to it as shown. The other follows along with it. And I want to find the angular velocity of the big one here, A, after this guy has rotated 10 revolutions. And I have mass and rate of gyrations shown there. So there's a few things I need to do before I apply my work energy equation. The first is the relationship between the angular velocities. So I just use the gear ratio, and I find that omega c is 1 1/3 times omega a. Okay, so I have that relationship. The other thing that I have is the moments of inertia. I just use the radius of gyration. So I take the radius of gyration squared times the mass of each one, and I get a moment of inertia of A and C as shown here. Okay, so now I'm going to go ahead and figure out my kinetic energy. So my kinetic energy will be both of the gears. So it's going to be 1/2 I omega squared A and well as C. Now there's no translation here. It's all rotation. So I just need the 1/2 I omega squared for each one of these. So I've got I, okay, and I put everything in terms of omega A using the omega I found over here. So I can find that the kinetic energy is basically 3.5 omega a squared for the two bodies. Okay. Next thing I'm going to do is talk about the work being done. Well, it's just the 50 Newton meters applied over 10 revolutions, which will be 20 pi, right? 10 times 2 pi. Okay, so the work being done is 1,000 pi. So now I can apply my kinetic energy. So it starts from rest. I do 1,000 pi of work, and my final kinetic energy is 3.5 omega a squared. I just solved that for omega a, and I get 29.8. So again, work energy, okay, so initial energy plus the work equals final energy. So I have my initial energy is 0 because it starts from rest. My final energy is basically 1/2 I omega squared of each of those added together. Okay, the work is basically the work of this moment. Put in there, you can calculate it that way.